This is your first actual lab project in this course. That doesn't mean you haven't already been working with hardware, software, the simulator. This is not the starting point for this course. The starting point was some number of lectures back where we covered all the basics. We laid all the groundwork to build you up to a point where when you got to the lab projects, you wouldn't be looking at things going, what's that? What's that? I haven't seen that before. So what we try to do is just to build up a solid platform or foundation for you to start doing work. Start to do your lab work. That would include, getting your laptop set up with CCW and RS links, reading the first couple of sections in the manual that aren't lab projects, watching the first group of videos, that's what does a PLC do, what does a PLC, inputs, outputs, ladder logic diagrams, etc. And then there were also a couple lectures on RS links specifically. Now, you can squeeze by without watching all that. Okay, if you did not attend those lectures, you should go back and attend them or watch the recordings. Otherwise, you can continue from here, but you're liable to step into a few stinky spots if you don't go back and make sure you've got all the bases covered. But if you pursue from here and you're comfortable, great. So let's talk about Lab Project M1. Now I'm kind of looking at it here, and what it's going to do is it's going to take you into the environment of Connected Components Workbench, having created a project. And the title is Explore Your First Project for a Micro 800. So we take you in with the bare bones project, no processor, no programs, nothing other than just you picked a processor, instantiated it, and now you're going in and exploring. So that's what we're going to do. Now, if you have not already done this lab, you can pause the lecture and go do the lab project, or you can continue through the lecture, then go do the lab project, and then come back and watch the lecture again. I strongly encourage you not to move on to another subject or lab project until you feel really comfortable with what you've done so far. Okay, so pause, or let's just jump in and start talking about the first lab project, M1. We're at approximate page 70 in the part 1 of the Connected Components Workbench Manual with Micro 800, second edition. Page name could change in the future, but for right now it's page 70. And in the manual, we did all of the lab projects with actual hardware, actual PLCs. Initially with some Micro 810s, then we went to 820, and then 850. We're going to do all of these projects primarily with the simulator, first of all to make sure that they all work well with the simulator and to firmly demonstrate the simulator. Because with version 12 with the simulator, you can actually do all these lab projects without actually having a controller. And that does save you a few bucks. Now, if you have the standard edition, you can look up on the screen and see I have the developer edition up at the top, above it in the title bar. But that gets you, the developer edition gets you 24 hours without resetting the simulator. With the standard edition, which is free is good, you get 10 minutes. So that means every 10 minutes, you don't lose everything. You just have to restart the simulator more or less. And remember, the simulator occupies a space in the RAM of your computer that version 12 of Connected Components Workbench, when you instantiate the simulator, it sets it aside and makes it look like it's an actual controller's memory. I've already added the Micro 850 simulator to my project. You can see it in the background, but I brought this up to show you what you pick. You go to Micro 850 when you create your project, go to Micro 850 and pick the one down at the bottom. It says -SIM. Now you can see over here, it says only one controller is allowed in the project. That's also a good thing to know. In a project, you can only have one controller. Now you can have more than one of other things, but not a controller. So I'm going to cancel this and then go back to the manual. The first thing we did in the manual was to look at the global variables. So we double click to open them. Now this is a 48 fixed IO controller, And in the manual, we may have used the Micro 810, which has only a few. Looking at this list right here, you see I/O, embedded, digital output, 0, 1, 2, 3, and so forth, all the way down to 19, which means you have 20 digital outputs to work with this controller. If we scroll down, and there's always more inputs than outputs, because traditionally you use 2 inputs for every 1 output. In other words, it takes more information to make a decision for a single decision. So you might have to look at 2 or more things to make a decision on whether to turn something on or off. That's just kind of convention. So now we scroll down and you see digital, well, I/O embedded, digital input 0 through 27. These are all in global tags, meaning that all of the programs that you write, and you can have multiple programs, each program has its own separate database, so you can actually have programs that are using the same tag names as other programs in your project. Each program only has access to its own program variables and the globals. So these are the globals, and these down here are all system variables. We're not even going to look at those. So that's what we did in the manual. We pointed this out. Another thing that we pointed out was before we opened the global system variables, we had just these 2 tabs. The start page, which you saw before you created, and then once you created it, the Micro 850, if you look close here, it says Micro 850 SIM, and you could scroll down, and all of this is going to look the same as the actual hardware controller by the same name without the -SIM on the end of it. But what I wanted to point out was as you open up things, more tabs appear up here. And you can actually move these tabs. They don't have to stay in the order that they pop up. You can kill the start page if you want. Matter of fact, you can turn them all off. Then you can bump them all back on by double clicking on things. The next thing that we had you do was to download this project. Now this is a bare naked project. There's nothing in it other than we created a data structure called Micro 850 SIM. The data structure that we created matches that controller. Embedded I/O, everything. Now we want to download it just so we can establish some communications with the controller. If you have an actual hardware controller, if you have it plugged in and powered up and the key switch or the switch in the remote position, meaning that you can communicate with it remotely, then you're most of the way there. All you have to do is establish the RS Links or FactoryTalk Links driver, and away you go. Not as simple with the simulator. I've already showed you this in other videos, but we'll do it again. First thing we have to do is say, well, we can't connect to something that's not there. We've created it, but we haven't powered it up. Well, the first thing you have to do is power it up. Up here in your, I guess you could say your simulator toolbar, you notice they're all grayed out except for one. That's your clue right there. So I'm going to start this by clicking on it, and it popped into the background. When it does that, if your simulator right in front of you, if it goes behind this screen, in other words, you accidentally click on this screen, then you're going, where's my simulator? Go down here and click on it, it'll pop it right back up in view. This is an important thing that you have to do, and that is your IP address. You drop that down. This is a little kludgy currently. It'll get cleaner as time goes on and more nuances pop up. I have my computer's NIC, my hardwired network interface controller that connects to an Ethernet cable. I have that set with a fixed IP of 100, 100, 100, 10. 100, 100, 100 is the address of the network, which means my subnet mask is 255, 255, 255, 0. The node on the network 100, 100, 100 that my computer is at is 10. So I'm going to click on that, and that technically sets up kind of a reflection from the software to the simulator because it's all in the same RAM. I also see that I have left on the simulator from a previous project, I have some wiring. So before I get too carried away here, I'm going to go to Device, Configure I/O Wiring, and I'm going to select this one, and I'm going to delete it. I don't want that in there. Now, in a later lab, we'll show you how to wire outputs back to inputs. This is just a pretty cool feature. And the fact that you have 48 I/O to work with, 28 in and 20 out, gives you a lot of extra I/O to play with to do some clever things. I've got it set, configured at 100, 100, 110. Now I'm going to turn it on. The simulator will run for 1 day. Yours is going to say 10 minutes. I'm going to say, okay. I can see I've already got some outputs on because there's a program in there. And that's something to keep in mind, is this simulator almost is a separate entity in the sense that this new project I created, there's no program in there. But the simulator, when I turn it on, comes up with the program that was last in there, just like a real controller would. And actually, I think that's pretty cool that they decided to do that. So now I'm going to connect. Notice that my simulator disappeared because it's not locked on top. So I'm going to connect to that simulator. Now see, my connection browser popped up. I'm going to go to AB Ethernet IP. There's my simulator. And remember, this is a 2080 LC5048 QWB. The S is your clue that that is a simulation. Right below it, you see another one of my learning stations that's an LC20QBB, and I've showed that to you in videos. And you see also that sometime in the past it saw this MicroLogix 1400, also one of my training units. I'm going to click on OK, and it's going to connect. See, up here it went from connect to disconnect. The current project content does not match the content in the connected controller. So I want to download the current project to the controller. I could upload the project to overwrite the current project content. I don't want to do that. So we're going to download to this puppy. And I will say that occasionally you may run into a bug where it locks up. This is happening less and less. Now here you have the choice between download or download with project values. It downloads just the program. The second choice is with project values. If I just do this, then the basic stuff downloads, but any data that's in there, result of timers, counters, etc., that does not get wiped out. Okay, you're just downloading everything but register values. If I download with project values, then I am overwriting any of the integer real values that would have been in the controller from the actual process that it's running. So download, we'll just say that's just the program. Download with project values, that's the program and the values in the register. We'll pick that simply because either way it wouldn't matter. Either one of those choices would end up with the same thing because our offline has no values. Change it back to the runs for 1 day. You're going to see that message every time you download. Every 10 minutes you're going to have to reset this if you're using the free version. And the free version is good. Okay, so we downloaded and we are now online with this simulation. So what we're going to look at next, or throughout all these projects, is exactly what it would look like if this were a real 48IO LC50. Next, I had you open up the global variables again. We can bring the simulator back on top. Another thing that we can do is we can make this a little smaller and make some room for the controller so we can see some of it. I can collapse this down to initial value. We can hide some of this stuff. In other words, we can pull in the alias just right off the top of my head, just for grins. Let's see if we can turn on this digital output. I turn that on, it stays on. The physical value went on. That's a verification that we selected an on state for this memory location. This is a memory location here, folks. This is not a screw terminal. This is in the memory. This is long before the optical isolator that goes out to the field wiring. We in the logic or in the data table said, turn that bit on. The physical value popped up later because it verified that down here, look down here, the simulator, you see 00 is orange. That's because it's on. You can see it's on right there, and you can see it's on right there. We turned it on. Now let's try the same thing with an input. So I'm going to have to scroll down so we can see input 0 there. And I'm going to toggle that on. With a real controller, you couldn't do this. Because with a real controller, if it's in the run mode, we're in the run mode. Look down there. Power, run, fault, force, com. We're in the run mode. Thousands of times a second. The firmware, the executive code in this processor is updating the input image with the state of the screw terminals. And if this were a real controller and there was nothing wired up to it, then screw terminal for input 0 would be low right now. It would be off. So you click to turn this memory location on, because remember, this is a memory location. That's not a screw terminal. So when I clicked on that to turn it on, it does go on. A thousandth of a second or even microseconds later, the I/O update is going to take place. It's going to see that screw terminal 0 is off, and it's going to turn off that bit in memory, even though you told it to turn on. That's with a real controller. This is a simulator, and this is the only way you have to control the inputs. Clicking on 00 there is simulating a field device that put a high value, like 24 volts DC, on the screw terminal for input 0. In the manual, we had you turn on the first 4 outputs. And if you have a hardware learning station, then your first 4 outputs should be on. If you're using the simulator like we're doing here, you can see that output 0, 1, 2, and 3 are on. Both in the data table here, logical value, physical value, and the simulated LEDs on the simulator. One of the very first things that we like to establish when we're introducing a controller, a processor, is the relationship between the I/O associated memory locations, in other words, those memory locations of which are updated by the screw terminal states on the inputs, and those memory locations that, if you're in the run mode, update the screw terminals on the outputs. In other words, turn them on or off. So you can see, just like in other controllers, if you turn on outputs with no code, in other words, there's no rungs of logic in there to overwrite the state of these output bits. What's going to vary between a hardware controller and this one is, with a hardware controller, the terminals for the inputs, they are at a voltage level, 0 or 24 volts DC, thereabouts. With a simulator, we simulate that voltage by clicking on the inputs. So if and let me scroll down to the inputs first. There we go, input 0 right there. So if I click on that, it doesn't stay on. It goes on, but then it's overridden on the very next scan. And the physical value never really comes on. You notice that? And the reason is because we're in the run mode, and when we click here, you directly change in the bit in memory. But if we go down here and turn on input 0, now you see it comes on and it stays on. So the answers in the manual are based on a hardware controller. Approximately page 73, did the checkbox change state? Yes, it did. Did it remain changed? No. That's based on a hardware controller. Why do you think that it behaved in this way? It behaved this way in the controller, or let me uncheck this and go up here and check it, because when you change the state of the bit in memory, the state of the screw terminal down here, which is 0, field device is off, every scan is going to write a 0 back into there. So even though you click, turn it on, the scan of the processor, when it updates the I/O, is going to write a 0 over it. The next thing we had you do was go to the controller and put it in the program mode. We could have done that right here. We could have went program and then back to remote. Same result. So we had you turn off, or rather switch to the program mode. The controller's now in the remote program mode. Can you make a guess at why the run and program choices in the software are grayed out? Okay, let's go back to our processor. Notice that these are now off. So if we go back to global variables and scroll up there, they're still on, right? We're connected, and this is reading the values. So in memory, these are on, but they're not being transferred out to the screw terminal. Now the physical values stay on because they were on at one time. So if we go down to the inputs now, and remember, we could turn on an input there, and we couldn't turn it on here. But see, we check it now, and it stays checked. The physical value doesn't change. But we can turn on that bit in memory, and notice that this shows logical values on, but it doesn't show it on here. Because remember, this represents the simulated state of the screw terminal, not the state of this bit in memory. So now we're demonstrating how it behaves with the I/O memory when it's in the program mode. In the manual, we ask you why the run and program choices. You see in the screen there, under the Micro 850 tab, you see Run Remote Program. We're in the program mode, but we're also in the remote. It's the state of the processor, but it's also a condition of the switch that controls the mode on the controller. So go down here and we'll put it in run. This is the simulator. It gives you the warning. See up here now it says run. We go back to program, or remote. Now it's remote run. We go to program. That switches it to the program mode. We go back to remote. It's in remote program. Those are grayed out because those really represent not just the state of the processor, but of that toggle switch on the processor. just to summarize, when we went to the program mode, the outputs were still on. Now I just did something that flipped them off, but I'll turn them back on here. Notice that the physical values don't check like they were before, because I did something by going back and forth between the run and program mode that when I was demonstrating that turned them off. Now if I go back to the run mode, this is another thing to know about this controller, this processor, that when you go from the program mode or any other condition to run, it automatically turns these off. Now I'm turning them on again, and you notice that the physical values stay on. We'll go back to the program mode and then back to remote, and you see they're not on. The actual physical outputs aren't on, but these stay checked. Let's go down and do the same thing for the inputs. Input 0, we check that, it stays on. If we go to the run mode, because this screw terminal down here, 0, has not been triggered on, then when it does the first I/O update, it will see this is 0 and change this up here to 0. The main difference between, see, I just turned this input on here. See, it has no effect right here. That's because there's no I/O update. It is different in a sense that you don't see the physical value. The upshot of this lab is that in the run mode, the screw terminal state right here, and I will put it back in the run mode, the screw terminal state determines the state of the memory location. Remember, this is a memory location, not a screw terminal. The screw terminal determines the state of the memory location in the run mode. The state of the screw terminal for an output is controlled by the memory location in the run mode. So in one case, the field wiring controls the state of the inputs, but the input bits are controlled by the screw terminal state. In the case of outputs, the screw terminal state is controlled by the memory location that it represents right here. So I can turn that on and see there it is right there. Okay, let's turn off that input and we'll turn off that output. Now what I had you do in the manual, and this is with a hardware controller, I had you turn on in the program mode a whole bunch of inputs and outputs. So we'll go down to where we can see some of each, and we'll turn on some outputs here. Now we're in the program mode, and none of these are turning on. Now we'll turn on some inputs, okay? Then I had you switch to the remote run mode. You notice instantly when it hit run, it turned those off. It turned the outputs off because that's part of the executive code for safety, is to turn the outputs off when you go to the first scan. Now the first scan can turn them right back on, so there's really no loss if that's what you wanted from the logic, but there is no logic here. And then it turned off all those bits that represent the screw terminal states for the inputs off because they're off. If they had been on, then they would have turned on here. So let's go back to the program mode and click a couple of these on. See, 0, 1, 2, 3, 4. See right here, nothing. Now if we go to the run mode, instantly they go on because the screw terminals are up to 24 volts DC. That's what we're simulating here, is the field wiring. Did all the boxes stay checked in the program mode? Yes, they did. What did they do when you switch to the run mode? All off. The outputs go off because that's a safety issue, and the inputs go off to make them match the state of the screw terminals. Now that's assuming that all of the toggle switches or push buttons attached to these inputs were off when you did this process, which they were supposed to be. A quick note, as was mentioned before, there has been an issue of the simulators faulting. Tech support said that if your computer was too fast, imagine that it could give you a watchdog timeout. Going in and extending the length of your watchdog timer, which that's something we haven't even covered yet, that really didn't fix it. Tech support said to go in to your configuration and reduce the number of processors that are executing for the simulator. Now we're going to show you how to do that right now. What I'm going to do is show you how to reset the fault. So you see my simulator is faulted. One thing I found that seems to cause faults most often is screensaver, or the computer going to sleep with the simulator run, you wake it up and it's faulted. There may be something to that. But look right here. See, this shows this is faulted, okay? I'm going to connect to it because right now we're disconnected. so I can't really diagnose the simulator if we're not connected. It took a while, but it's connected. And of course it comes up and says that the current project content doesn't match the content in the connected controller. It's the connected controller that we're concerned about, so we're going to upload. And we can use logical values. It really wouldn't make any difference in this case because we don't have any registers, wouldn't let us. So we will download then. This is good that this happened because sometimes it's hard to simulate these faults and then record it. I'm going to select download, so it's building the program. In other words, it's compiling it. Controller's faulted, continuing to download will clear the fault information. Okay, well, that's too bad. It's going to download and clear. I wanted to show you how to clear the fault. Basically, you'd go to diagnose, you would go to fault. It would come up with a fault code, and then you would clear the fault, which it's already cleared. So I guess that's the best we're going to be able to do with this situation. So here we are in our exploration moment. The main thing in the exploration moment, that was on roughly page 75, was for you to kind of summarize what you learned in this lab project. And so what's the difference between logical and physical values? Well, let me show you how these are used. We're in the run mode, okay? Now, if I go to an output, we'll scroll down here so we've got outputs and inputs. If I click on physical mode, nothing happened. Now, I don't have a program that has logic in it that's controlling this output bit, so I can turn it on and see down here, you can see 19 is on and 19 is on over here. So it shows that it's on. If I lock this, that's their form of forced I/O. So if I go back to the logical value and turn it off, I can't turn it off because it's locked. If I go to an input, see, I can turn on an input value, but it goes back off because this screw terminal 00 is off, therefore it overwrites during the scan. But if I go to lock, turn on the physical value, and turn on the logical value, notice the physical value is not on, but it's locked. And if I turn it on, see, physical value goes on, turn it off, physical value goes back off. So this is kind of how you use the physical value column. The purpose is really for how you execute forces. And you see the little orange force light right here because I've got something locked. If I unlock them, I see the force light goes out. The other use of the physical value is, and you see 19 is on right now, so the physical value is on. If I go to the program mode and back, it still shows it's on even though you look down here and you don't see it on. It's showing it on because on the last program scan during run, it was on. If I go back to the run mode, keep an eye on your physical and logical value as I click on run. See, it instantly went away. Go back to remote mode. So in your exploration moment, what's the difference between logical and physical values? Well, logical is the result of your logic or your code, or you directly clicking on these memory locations. Because remember, a logic wrong can turn on this bit right here, or I can click it on. So the logical value is based on either your logic or a direct intervention from your mouse. Whereas the physical value really reflects more about the screw terminal, or in the case of an output that was on and then you went to the program mode, it reflects the last state of that output. And then is there an instance where you would check the physical value box? No. You will not remember all these observations indefinitely, so I ask you to make some notes. This, an exploration moment, is where you just stop right here and you keep playing with the logical value, the lock, turning on inputs, changing modes until you get a good feel for the relationship between the logical and the physical value. But primarily, the physical value is used with the lock column to force inputs and outputs off and on. So right now, I've got, these are both off, so I'm going to lock these two, okay? Now I'm going to try to turn on output 19. I can't, see, it's locked off. I'll try to turn on input 0 here. You see the physical value comes on, but the logical value does not. So you need to exercise these things until it's clear in your head what you can do with this part of your graphical user interface. What did we do in this first lab project? We introduced you to the graphical user interface, connected components workbench, created a project, and in the project added a controller. In this case, it's a 48 I/O controller, but it's the simulation of the controller. And remember, the heart of any PLC is its random access memory. Everything takes place in the random access memory. When you create a simulation of a controller, 99% of it is the memory. So we just take a chunk of RAM right in your computer and set it aside. We add some methods and some vehicles to it so it can behave identically to a controller. Then we started looking closer at RAM, primarily at the behavior of the memory locations in RAM that are set aside to show you the state of the inputs and for you to declare the state of the outputs that you would like. Meaning you collect up the state of the screw terminals, the input screw terminals, you put those in memory locations. Then you execute your logic, and when you execute the logic, you set the state of other bits in memory that when the logic has been executed, the controller, or the processor rather, takes the state of those bits in memory and sends them out and changes the state of screw terminals on outputs. The relationship between executing the firmware or executive software of the processor, meaning running it, putting it in the run mode, behaves differently towards memory locations set aside to give you the state of the screw terminals of the input interface, the field wiring from input devices, and yet another unique relationship with the bits of memory that are going to end up being the state of the screw terminals for the outputs. 3 areas of memory you have to be concerned with: the input image, all the other bits of memory that are not inputs or outputs, and then the outputs. Now, there's going to be some memory locations for things like real-time clock, status. These are fixed memory locations. You don't create these. When you create a project with a particular processor, it creates a data image of that processor right in your RAM, and then you execute it. So that's what we did in the first lab. Probably the most important thing that we examined in this first lab, Project M1, really, we were exploring what is there before you actually add something. In other words, you created a project with a controller, whether it's the simulator or a hardware controller of your own. You created a project, but there is no connection between the project that you created and the simulator or the controller other than what's implied. There's not been any connection made. Nothing's been uploaded, downloaded. So you're starting with a bare bones project. And we go in and look at really the only thing there is to look at, and that is the global variables. The global variables include all the I/O variables. The I/O variables are probably the most notable of the global variables to begin with, because everybody, where's the inputs, where's the outputs? So we kind of covered that base. And towards the end of the project, and I'm kind of looking at the manual here, and we had a exploration moment where let me get to that section, where you were looking at the difference between logical and physical. This is a really important point because the physical would be the screw terminals. And of course, you don't see physical value for inputs because the module defined data types, that would be the data types that are defined by the specific hardware structure of inputs and outputs. Those are predetermined. You cannot edit those. You can see the values that result, but you can't edit them. You can't touch them. Okay? So if your processor is running, it's in the run mode and running, it's going to update those memory locations based on what's at the screw terminal on the controller or the I/O modules, if you have expansion or snap-in modules. The output screw terminals are the physical value that was in that one column. So there's logical value and physical value. Logical value is based on the state of that bit in memory. Physical value implies that the screw terminal is 1 or 0, on or off, high or low. So that should have been the primary thing that you learned from M1. The next lab project, M2, you're going to take it one step further, and you're actually going to add something of your own to see how So you can experience doing something, adding something to the program, downloading it, and executing it. This will be your first experience of seeing if what you expected is what you got. And this will tune you up as you go. So that's it for M1. We'll see you in the M2 lecture discussion. In the meantime, if you want to do M2 before you watch M2 lecture discussion, that's great.